Oh, before I get into that, uh, the exam, I meant to double check, but I think it's a week from today, exam 3. Wednesday. Yes, you could. So, yeah, these 50-minute tests are, it's tough to do like a linkage test in 50 minutes. The topics, though, are everything. Yeah, up through, not everything, everything up through. Um, and yeah, linkages take so long. Most likely, I will isolate like a part of a linkage problem. Like I'll say, um, come up with Newton's laws for these bodies or something, and then uh, tell me how many constraints you need. You know, like I could ask a question like that, or I could say, um, yes, exactly. I could say, come. I could give you um, the Newton's laws equations and say, come up with the constraint equations. Uh, so, and I think it's safe to say that I will not make you solve any systems of equations. I'll just make you come up with the systems. Um, so that's the kind of stuff I can do to make a little more time, so it's not just one single problem and you're still just racing to finish it. You know. But you should be ready for all the other kinds of problems too. Uh, any questions about the test? So what do we have? Two more class periods before the test. So if you have questions about linkages or anything before that, bring them, and I'd be happy to talk about those. We're going to finish this one linkage problem today. Oh, we haven't done linkage problems like you guys doing linkage problems in groups on the board yet, have you? Let's do one like that before we move on to the next thing. But I like the next thing is the coolest topic, the best topic in any class. Figuring out um, how to use Newton's laws when the coordinate system is non-inertial. Yes. 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 Yep. Right. And I think it'll all be, I think there's only 9 of them or something, so I think they'll all be assigned by then. Well, I mean, you got to do them to get ready for the test anyway, so you might as well turn them in. Well, life's hard everywhere. Um, what? Yeah. Oh, yeah. 6 members. That's correct. So the next topic we get into is not on this test. Okay, so last time we were working on this example. Where we had 2 members like this. This is the one that was supposed to uh, sort of look a little bit like possibly a um, biomechanics problem. This angle is 45 degrees. This angle is 45 degrees. Member 1 and member 2. And I labeled the joints A, B, and then C up here at the top. this instant, both of the angular velocities were the same. They were moving clockwise, so negative 10 radians per second. And then external couples were applied. We had one of positive 20 Newton meters on body 1 and negative 20 Newton meters on body 2. The two lengths were each 0.5. And the two masses were each 5 kilograms. And we want to calculate the acceleration of the point C. Okay, so isolating member 1 gave us how many equations, how many Newton's law equations? You should actually, so don't look back, just see if you can figure out what's going to happen with this member. One equation, so why will that only give us one equation and not 3? Exactly, it has a fixed point, so we don't use Newton's second law. And then isolating member 2 will give how many equations? 3, that's because that one does not have a fixed point. So we have a total of 4 equations after Newton's laws. Without thinking about what the variables are, how many constraint equations are we going to need? We're going to need 2 constraint equations, and the reason is there's only one joint that's not fixed. So the constraint just says the acceleration vector, and it's a 2D problem, so a vector is 2D. The acceleration vector according to this has to match this. So based on what kind of joints you have, you can figure out at a glance how many constraints you're going to need. And that those constraint equations are the x and y components of something that says the acceleration of b, according to member 1, has to be equal to the acceleration of b according to member 2. So we end up with, in this case, 6 equations for 6 variables. We wrote out the matrix last time, and if you solve it, I didn't write down any of the forces or anything, but you get that alpha 1 is equal to 33.87 radians per second squared. And alpha 2 is negative 177.28 radians per second squared. Oh, shoot. We need the, well, okay, well, we're going to have to do a little workaround then. So that's okay. What? We made an error? We just didn't get it done. We just ran out of time.
Yeah, you're talking about instead of the whatever number we had.
Yeah. Okay. Yeah, 53.02, but that's what I used. Okay, so we corrected that. All right, so I think these are right. Okay, well, So now what we have to do, the final step, is to calculate the acceleration of that point C. Well, if I'd written down the answers for A2, you know, the acceleration of the center of mass of 2, we could think of AC relative to the ground as being the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground, where this one is A2, and this one comes from circular motion. But I didn't write that down. So how can we do this? Yeah, so we're going to have to use relative motion again. So what we're going to have to do is we're going to calculate the acceleration of C relative to the ground as the acceleration of C relative to B plus the acceleration of B relative to the ground. Where this one is the circular motion of B around A, and this one is the circular motion of C around B. Yes. So this circular motion, the acceleration of B relative to the ground, is going to depend on the angular quantities of body 1. This one is going to depend on the angular quantities of body 2. Who's with me on this? So we're trying to calculate the acceleration of that. We're going to first calculate the acceleration of B according to that circular motion. And then we're going to assume that B is fixed, suppose B is fixed, and calculate the circular motion of this around B, and then add those according to relative motion. Okay, so first, what's the acceleration of B? So the acceleration of B is equal to alpha 1 cross the r vector that goes from the center of the circle to the point, so 2b from A, plus omega 1 cross quantity omega 1 cross r dA. Alpha 1 is equal to 0033.87. Omega 1 was given at the start of the problem, 0, 0, negative 10. And R going 2b from A is 0.3535, 0.35350. So the acceleration of B, this is relative to the ground, is equal to 33.87 crossed with 0.3535, 0.35350 plus 0, -10 cross quantity 0, -10 cross 0.3535, 0.35350. And could someone calculate that? -47.32. Okay, I'll leave it like that. Okay.
Something like a test, is it fine if we just write out like initial equation,
Yeah.
i.e. the first line and the values for them?
Yes.
And just write.
Yeah, that's perfectly good. And I'll just assume you have it programmed into your
That's
calculator.
what I always do.
Yeah, that's great. Yeah, that's perfect. How could its acceleration be in that direction? Does that make sense? What do we know about its acceleration? It's got tangential and centripetal. Which way would the tangential be? It has to be tangent to this path of the red circle. Its angular acceleration is counterclockwise, so its tangential acceleration is that way. Its centripetal acceleration is that way. And so, yeah, I mean, we don't really have a way to check the numbers, but you can get the vector that we got with vectors in those two directions. And now we have to calculate the acceleration of C relative to B. So now we're assuming that B is fixed and body 2 is rotating around B. So this is going to be alpha 2 crossed with R from the center of that circular motion to the point we care about. That's R going to C from B, plus omega 2 cross quantity omega 2 cross R to C from B. Alpha 2 is 0, negative 117.28. Omega 2 is 0, negative 10. And R2C from B is negative 0.3535, positive 0.35350. And so could someone punch in the acceleration of C relative to B? Okay. Wait, 98.018502. Okay.
And then 27.
Okay. And then 0. So the final acceleration of the point C is the acceleration of C relative to B plus the acceleration of B relative to the ground. So 98.02, 27.32 plus negative 47.32. Negative 23.38. And could someone add those two up? 50.70.
That's not right. I must have put something wrong.
It's not?
Oh, sorry, no, it is.
Okay.
It's negative. Okay, and then 3.9 for 0.
Okay. So the acceleration of that point C is, 51.4 meters per second squared. So in this position, if the leg is in this position, and everything's rotating clockwise, and you fire this quadricep muscle really hard to straighten out the knee, you get a big horizontal acceleration, a smaller upward acceleration, and that's the kind of analysis that you do in like sports type research, like how would you optimize this motion you want to achieve, with you activate this muscle at this time or this muscle at this time, how do you get the thing you're trying to do? It's also the kind of thing that people would look at before they do orthopedic surgeries, like if we affect the muscle's ability to do this at this time, how is that going to affect the leg's ability to get the foot off the ground as it swings through, or that kind of thing. Any questions about that? Okay. Well, let's do an example where you can work together and hopefully sort of straighten some of these ideas out in your own head. So let's think of this as like two bodies. Let's say this one at this instant, well, this is 1, and this is 2. Let's say the length of 1 is 1 meter. The length of 2 is half a meter. Let's say the angular velocity at this instant of body 1 is positive 5 radians per second. And the angular velocity of body 2 is negative 30 radians per second. So the top one's spinning a lot faster. And at this instant, let's figure out the acceleration of that point C. That's right. Yep, that's right. Okay, any questions about that?